In this video, we're going to look at an example of a derivative where we have to use the product rule within a quotient rule. So we look at the overall structure of the function first, and we see that it's a quotient, so that's going to be quotient rule. But notice in the numerator and denominator we have products, so within it we're going to use the product rule. So I'm going to do this in a couple of steps so you can see the setup. So when we go to calculate our dy dx, we leave the denominator alone. So sine x cosine x times the derivative with respect to x of the numerator, x squared e to the x. We'll take that derivative in the next step. Quotient rule is minus. Well, that's why the order matters. And so now we leave the numerator alone, x squared e to the x, and then times the derivative of sine x cosine x. And this all goes over whatever the denominator is squared. You don't change the denominator, you just square it. So sine x times cosine x, that whole quantity squared. Now we'll involve the product rules. Similar to the numerator of the quotient rule, except it's going to be plus. So the sine x cosine x is done. It's part of our answer. Now, here we do the product rule. I like to leave the first part alone, times the derivative of the second. So again, let's do this in a couple steps. d dx of e to the x plus now e to the x times the derivative of the other part. So times the derivative of x squared. Minus, now we leave the x squared e to the x alone. And now we're going to apply the product rule in here. So that's sine x times the derivative of cosine x. Plus, now we're leaving cosine x alone, times the derivative of sine x. So this is a little bit more drawn out than you might do when you're working your own problems, but I want you to just see the structure. We can distribute that square and write this as sine squared x cosine squared x. We'll see if there's any canceling we can do. This is going to probably be a little messy, so there might not be, but we'll take a look. So we have the sine x cosine x. Now we have to take the derivatives of our product rule. So x squared, derivative of e to the x is e to the x. The e to the x is already done. The derivative of x squared is 2x. And then we got minus x squared e to the x. Sine x, and then times the derivative of cosine x, which is a negative sine x, plus cosine x times the derivative of sine x, which is another cosine x. So now all our derivatives are taken. Only other thing we can do now is any possible cleanup. There's not going to be much we can do on this one. We could factor in x and an e to the x out of them. We're not going to be able to factor a sine or a cosine out, so that's not going to give us much canceling. But we'll pull out what we can. But I do want to emphasize this is the correct derivative. What we're doing from here on out is just any simplifying that's possible. For instance, I can pull an x and an e to the x out of both of these. So x e to the x. We still get left with the sine x cosine x here. Here we pulled out an x e to the x. So what would we get left with? We'd get left with an x for this term and a 2 for this term. Then minus, now we pulled out an x and an e to the x, so that becomes just an x. And then inside these parentheses, we've got a negative sine squared x plus cosine squared x. Because the sine is negative, the sine squared is negative, that does not allow us to use our Pythagorean identity there. We could use a Pythagorean identity and combine the sine squareds. Again, we're not going to be able to do too much more simplifying. There's not going to be anything that cancels. So all over sine squared x cosine squared x. So that's enough simplifying for right now. Depending on what we were trying to do, we could go further. We can see that, for instance, 0 for x makes the numerator 0, which makes the whole thing 0, but it also makes it undefined. So would be a critical point if we're doing optimization. But the main goal of this video was to show you how to get to the derivative and then just look at some possible simplifying.